And there's okay, there's a question on the back channel chat. It says, sir, are we trying to achieve, what are we trying to achieve with density matrix? Okay. So right, so you had a tutorial on density matrix, and the density matrix, the idea was that if you have like a, suppose you have a collection of states which are given by, say, psi1, psi2, dot, 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 psi n, and you are given a probability that the particle or the system is in state psi1 with probability p1, psi2 with probability p2, dot, 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 pn, right? Then you want to describe this physical situation, and the idea is that the only way you can describe this physical situation is via a density matrix. And in the tutorial, you were told that, okay, you took, say, you took an example of this where you took two states, say, x plus, or sorry, not x plus, say z, z plus and z minus, right? And this had a probability of occurring with probability p, and this was 1 minus p. Now, the thing is that if you measure S of z, then how are you going to model it? One way of modeling it is to actually do, say, okay, we have a density matrix, and then we have z plus, with p probability here and 1 minus p here, and then z minus, z minus. So this is one way of doing it, and this is the correct way of doing it. But you might say, okay, well, this statistics, this probability is also, replicated if instead of a density matrix, we take a pure state. So this is not a pure state. Not a pure state in general, right? For generic P, for generic values of P, this is not a pure state. If P was 1, of course, this term would vanish, then this would be a pure state. If P was 0, then this term would vanish, and this would survive, then it would be a pure state. But for generic values of P, it is not a pure state. So you might say, okay, well, I mean, this statistics is, I can replicate it by taking a state which is a pure state where the coefficients of superposition or linear combination is this. You might say that this works. And it does work as long as you are observing Sz. But suppose that instead of observing Sz on this set of state particles, I decide to observe S of x. Then what happens?
Sir, shouldn't one of those be z minus?
Yeah. Okay. Sorry, I'm just going to let the dog in. He's crying for some strange reason. I want to. Anyway. So we have a new student. He's a dog. Okay, sit down. So yeah, you're right. So now, but if I say I want to measure Sx, then it's easy to show, or it is possible to show that this gives you the right statistics, whereas this doesn't. Okay, and that is the point of the tutorial. So I don't want to go through the rest of the tutorial right now, but just point out one thing is that let's look at this. So z plus can be expressed in terms of x here, x plus and x minus. I think that is the correct linear combination. There may be some i's or stuff, which is not important for my analysis here. And the other one is going to be a different linear combination. And the thing is that if you're measuring Sx, then if the particle that we get is in state Z plus, so the probability of that happening is P. Of that, the probability of getting X plus is half. So we get probability of P by 2 of getting X plus. But in case we get the particle Z minus, the probability, oh, somebody wants to join, okay. Okay. Abhijit, can you like accept the invitation from the calendar? That way I don't have to let you in every time. Okay. Anyway, so in case, the particle is Z minus, then the probability of X plus happening is what? Somebody tell me.
Z
Half.
plus
1 minus P divided by 2, right? So if I add these two, what do I get? I get half. So if I decide to measure Sx, half of the time I get spin up X plus, and half of the time I get spin down X, in the state X plus. Now, do I get the same? And here we are not using any density matrix argument or anything. We are using a physical argument. So this is correct. Now the idea is that, does the mathematics here work out? Well, if I express this now in terms of X plus and X minus, what do I get? I get square root of P plus 1 minus this divided by 2 X plus, and I get square root of P minus 1 minus P divided by 2 X minus, which is not a P independent probability. So we see that we get a different probability if I use this one. And then the rest of the density matrix tutorial was like, how do we extract the probability from this, the mathematics, which of course should give you half. Okay. All right. So I hope that clears that up. So the density matrix is the most general way of representing probability of a quantum system. It includes both quantum probability as well as classical probability. That's the idea, okay?
Sir, on lecture 16 and lecture 17, the first few pages are the same. Is that normal?
Yeah, that's basically because I basically ran out of time for lecture 16, and part of it was used for lecture 17. Yeah. Okay.
So if I study lecture 17, I don't have to study lecture 16.
I think so. Yeah.
Oh, okay. Thank you.
Yeah.
I guess my question with respect to these density matrices is that what is the difference between the situation where we can just use pure states and when we have to use mixed states?
Well, when you can use a pure state when there's only one of these guys.
So when there's only one probability involved.
Yeah, well, when there's when the state is when you're sure of the state, yeah.
Also, each state is 100% probable.
Yeah, or one state. You have only one state.
Oh, I see. Okay.
Yeah. Because even that state has quantum uncertainty, right? Because if I take, for example, a state psi, and this is a pure state, and this is given by C1, say Z plus C2, Z minus, and this is normalized, say, then if I measure S of Z, the probability of me getting spin up is, C1 squared, and the probability of me getting spin down is C2 squared. So even there is probability, but this is the quantum probability. And this is known as a coherent superposition. Okay? And the density matrix describes the thermal ensemble, or when you have, or a canonical ensemble. So if you have a quantum system and its energy is given by E of n, so the particle is in the state En, then the density matrix for that is given by e to the power minus beta En, and summed over n divided by n e to the power beta En, right? This is the quantum version of the canonical ensemble, okay? And this is the density matrix because, these are probabilities. These are classical probabilities. Okay, so let's carry on. And do we have more questions or about this?